Hey everyone, this is Nadeem and welcome to my YouTube channel. Today in this lecture, we will discuss in more detail about semiconductors. Semiconductors are materials which have conductivity between insulator and the conductors. Such type of materials is used for many applications in our daily life. One of the semiconductor device is the diode, which is used for the conversion of alternating current into DC. The chargers which is used for our mobile, this is actually convert the alternating current into DC, okay, the direct current. Inside that charger we have such semiconductor devices which help us in order to do so. Similarly, we have the you may hear about transistors, which is the building block of our modern technology. Okay, the CPU inside the CPU of our computer, we have millions and billions of the transistors. Transistor is actually this semiconductor device which have mainly two functionality. One of them is switching. Okay, it is used for switching purposes. Okay, in the computer, okay, we have the compiler which is used for the encoding. Okay, so during that encoding process, we have 0 and 1, the binary numbers. That binary numbers is actually originated from these semiconductor devices, which is from the semiconductor device which is called the transistor. Okay, so long story short, these semiconductor materials, including diode, transistor, and other type of the semiconductor materials, have many application in the modern technology. In this lecture, we will discuss the overall theory behind that semiconductor materials. Okay, so here in semiconductor material, we have two types. Okay, one is the intrinsic semiconductor, the other one is the extrinsic semiconductors. As here the name intrinsic represent the power. Okay, if we consider the chip, okay, that is made up of the silicon is actually the element of the group 4, okay, having 4 valence electron, and here is that representation. This is the silicon chip. Okay, inside their crystal only the silicon atom is present. Okay, so therefore we call this as intrinsic semiconductor. Intrinsic semiconductor consists of only one element, and in daily life we do not have such ideal case in which there is no impurity atom. Okay, so due to some crystal defect or any other impurities, there is some atom may be present inside this silicon crystal. So about one atom out of billion, if there is one impurity atom out of billion silicon atom, then that is also considered as a intrinsic semiconductor. Here let's consider this is a silicon atom. Silicon atom belong to the group 4, having 4 valence electrons. And if one silicon atom share their electrons with these surrounding 4 silicon atoms, it will complete their octet, their 8 electrons in the valence shell, and will follow the octet rule. Okay, so this is that same scenario, and all these electrons are bound to their atoms, mean that all these electrons are in the valence band of their energy band diagram. So this is actually that energy band diagram, and all electrons at 0 Kelvin, at very low temperature, all valence electrons are strongly bound to their atoms. They all are strongly bound to their atom. They are not free. There is no electron in the conduction band. Okay, so therefore at 0 Kelvin, this intrinsic semiconductor is behave as an insulator. Now we do not have the electron which is free for the conductivity, and here it is behave as an insulator. Now what will happen if we provide the external heat to this material? That external heat will be used to break this atom, okay, in order to exceed their binding energy, okay. In other words, we call that binding energy as a band gap. If we provide about 1.1 electron volt energy to this material, the silicon bond will be break, okay. So if that is break, the electron will free from here, from this bond, and it will be go towards the conduction band, and here in this region it will leave the hole behind, okay. Hole is actually quasi static positive charge, so it that will be remain here in their own position, okay. It represents the vacancy of electron, and that electron has jumped to the conduction band due to the provided temperature, okay. And this is the band gap for weight, okay. So if we provide the external temperature, if we provide the external temperature, the electrons will be jump from the valence band to conduction band. In other words, if we provide the external temperature to this materials, the bond will be break and the electron will be free, okay. That free electron will be present in the conduction band, and behind that original position, in this valence band, the holes will be present, and so the hole will be present in the valence band and the electrons will be in conduction band. So for each hole we have one electron, okay. So for this hole we have this electron, for this hole we have this electron. So in other words, we can say that in this intrinsic semiconductor, the number of these holes will be equal to the number of the electrons in the conduction band. So the number of the holes in the valence band, which is actually 4, is equal to the number of the electrons in the conduction band, which is also the 4, okay. So in more technical word, we can say that the density of the electrons in the conduction band is equal to the density of holes in the valence band. So here in the valence band, these holes, if we provide the external battery to this intrinsic semiconductor, okay, so to this material, to this intrinsic semiconductor, if we provide the battery, this side become the negative and this side become the positive, okay. This due to this negative charge, due to the electric field from this cathode, that electrons present inside this silicon chip, that electron will be moved away from this negative charge and will be attracted toward this positive charge, and hence the electrons will be moved from the left side towards the right side. The conduction, the direction of the electrons inside this silicon crystal will from left to right. On the other hand, if the electron is moved in this way, okay, here the electron will be if that electron fill this hole, here the hole will be present behind there. So in the other word, we can say that we have this positive charge and this is the negative charge, and hole is actually quasi static particle with the positive charge, okay. That holes will be repelled from this side and will be attracted toward this negative cathode, okay. So from here we can say that the holes move in opposite direction, which is from left to right, okay, and the electron will be move in the opposite direction to that hole, which is from right to left. So here this electron is moved from right to left, and these holes is moved from the left to right, okay. So holes move in opposite direction to that of electron in the intrinsic semiconductor. Now, what is extrinsic semiconductor? Is here the name represent the impure semiconductor, mean that just like in previous crystal, we have all the silicon atom. Now in an extrinsic semiconductor, we will add some impurity from the group 3 or group 4 group 5 element into these silicon crystal, so it will not remain as a pure. Now it will become the impure. Okay, so in order to enhance their conductivity, we compel to add the impurity atom into that pure silicon crystal. Okay, so the process of addition of the impurity into that intrinsic semiconductor is called the doping. Okay, and the atoms are the element which has to be added into that silicon crystal is called the dopant. Okay, so why we are going to do that, and we are going to add the impurity into the silicon crystal, which is because we are interested to increase the conductivity of that silicon crystal. Okay, so the atom which we are going to add to the silicon crystal, we call them as a dopant, will have the same size, comparably the same size as that of the silicon crystal, because it do not have to distort the crystal structure and produce the crystal defects. Okay, so this is that scenario. We have all these silicon crystal and we have added this element which is from the group 5 and consider that is to be phosphorus. If we add phosphorus atom into the silicon crystal, so that is that scenario. The phosphorus have the 5, this is pentavalent and having the 5 electrons in the valence shell. 4 of them will be shared with the surrounded silicon. Okay, and 1 of them will be remaining here. Okay, so this electron is responsible for the conductivity. This electron will enhance the conductivity of that intrinsic semiconductor. Now we have this electron in majority here, so therefore we call this sort of material as n-type semiconductor. We have electrons in majority here. Okay, so before adding this dopant have the valence 5 electrons. Okay, now that 4 of them has shared and 1 is still free, so therefore we call this element as a donor core. It will on top of it we have the positive charge appear, and therefore we call that as a donor core, and this is that free electron. Okay, and these all are the silicon crystal. Okay, so the here these electron has produced without producing the hole in this crystal. Hole is actually the quasi-static particle, as I have discussed, and which is actually represent the vacancy of electrons and having positive charge. So if we see the macroscopic structure of that n-type material is see like this. Okay, so here this positive this is the positive core and these are the negative core, and here these positive core represent the donor core, which is actually phosphorus. And the energy band diagram for the n-type material is given by this. We have the valence band, this is actually that conduction band, and here we have add the element from the group 5 into the group 4 crystal. So we have 1 electron in excess, so that 1 electron will produce the another discrete energy level in the energy band diagram, which is given by this, and which is near to the conduction band. Here the band gap between this discrete energy level and this conduction band is very little. Okay, so here in this case, if we provide at 0 Kelvin, this p-type material still do not conduct electricity, because here that excess electron is not present in the conduction band. It has made the separate discrete energy level, and that is present here in that discrete energy level that is not present in the conduction band. So therefore it's zero Kelvin. These electrons do this entire materials do not conduct electricity. Now if we increase the external temperature to this, so if we increase the external temperature from 0 Kelvin, okay, so all these electrons, here the band gap is less, all these electron will uh, take that energy from the heat and will jump into the conduction band. All these electrons will be jump into the conduction band, and similarly some of the heat will be used to break this bond. Okay, so due to that, when that bond is break, the electron will be jump into that conduction band and will leave the hole here. Okay, so this is that valence electrons which is bound to the atom. These also absorb the heat and will be transferred to the conduction band. Okay, so here these two, consider these two electrons have taken enough energy from the external heat and have jumped to the conduction band from the valence band. Okay, so here we have this electron is in excess because in this level we have large number of electrons, that all electrons has shifted towards this conduction band. Okay, and it do not produce the hole here because these electron is contributed by this pentavalent element, and this electron has produced without producing the holes in the valence band. So therefore all these electrons have jumped into the conduction band, and two of them, these electrons, are come from the valence band. Okay, so here the overall number of electrons in the conduction band at some temperature T is greater than the hole present in the valence band. So therefore the conductivity, so therefore this electron in the n-type materials are called the majority charge carrier, and this hole is called the minority charge carrier. Okay, so this is less in number, and these holes in is if we provide the external battery to this materials, and that in this material the holes will be start motion in the valence band, and the electrons which is in majority will start motion in the conduction band. Okay, so that electron is more in the conduction band, so therefore we call these electrons as a majority charge carriers, and these electrons are minority charged carrier. Okay, so at slightly high temperature, the donor electrons populate the conduction band, and for the reason behind that I have discussed. Okay, so why they are populated there? Because here this band gap is very less. The band gap between this separate energy state and this conduction band is very less as compared to the band gap of this valence band and conduction band. So therefore by increasing little bit external energy, all electrons will be available for the conductions in the conduction band. Okay, so at that ordinary temperature, okay, some electrons from the valence band excited into the conduction band, and if we increase the temperature, these electron has already gone to this conduction band, and if we increase the temperature, some of these electron will also jump, and that electron amount of that electron will be more, and here in the valence band the amount of the holes will be more, and the conduction of this material will be more. Okay, so That was all about the N-type semiconductor. Now we have the P-type semiconductor. In P-type semiconductor, we will use the element from the group 3 and will add that into group 4, which is silicon atom. So in the simple words, we can say that if we have the silicon crystal, okay, so we are going to take the element from the group 3, which is actually boron, and adding them into this silicon crystal. Okay. So in that case, that boron having 3 valence electron because that belongs to group 3. The On the other hand, we have silicons in this silicon crystal having 4 valence electrons. So when these 3 electrons are shared with their electrons with the surrounded silicon atoms, okay, the overall number will be 7 because here the valence electron of this phosphorus is 3. The valence electron of this the valence electron of this boron is 3 and the valence electron of this silicon is 4. If we add them, it will become 7. Okay. The octet rule is not follow. Here we have the vacancy of 1 electron and we call that vacancy as a whole. So therefore, the whole is present here without the electrons in the conduction band. Okay. So therefore, this atom required some data of the electron required some data of electron. So therefore, we call this element, this dopant, this boron is the acceptor core and having that hole without producing the electron. Okay. So here is no electron hole pair production. Okay, this hole is actually come from that intrinsic process. Okay, present here because the valence electron is now 7 and it required 1 electron. So therefore, this hole represent that requirement of the electron. Okay, so in macroscopic level, if we see this such type, the process will be appear mean that we have these negative charges, okay, and having that positive charges. So this is actually that acceptor core, and this is the macroscopic view of this. Okay. Now, the energy band diagram for this is just opposite of that we have discussed in the N-type semiconductors. Okay, but the difference is that in the N-type semiconductor, we have the electrons in majority. So therefore, that electron will be present near to this conduction band. And now here in this case, we have the hole present in this crystal, and that holes will be present at at 0 Kelvin, at very low temperature, at 0 Kelvin, all these electrons will be present in the discrete energy level that is near to this valence band. Okay, that is near to this valence band. So in the other word, we can say that at 0 Kelvin, this crystal, which consists of the impure atom, still do not conduct electricity because here in the valence band we have no holes, in the conduction band we have no electron. So the conductivity of the semiconductor is actually due to the holes in the valence band and the electrons in the conduction band. Both are absent here in this condition at 0 Kelvin. So therefore, the p-type material still do not conduct electricity at 0 Kelvin. Okay. Now, if we provide some of the energy from the external temperature, here the band gap is less. These all holes will be jump into the valence band. Okay, all holes will jump into the valence band, and here the amount of the holes in the valence band is more. And from where these two electrons come? These two electrons again come from if we provide the temperature to this crystal, which consists the dopant as well. Okay, if we increase the temperature, in this case, this bond may be bond. This bond may be break in, or if they absorb the energy, the band gap energy, this bond will be break. Okay, so some of electron will be produced, and that electron will jump into the conduction band and will leave the hole behind in the valence band. So these electron have jumped to the conduction band in the presence of external temperature. Okay, and these they have left the hole behind here in the valence band. Here the amount of the hole is more in the valence band as compared to the electrons in the conduction band. This is because of this dopant. Okay, their dopant have their intrinsic holes, and the physics behind that we have discussed. Okay, so therefore the holes here in the valence band is in majority charge carrier in p-type materials, and the electrons in minority charge carrier. Okay, so at very low temperature, this is behave as an insulator. At ordinary temperature, hole produced due to the intrinsic process and also by heat and go to the the electrons has goes to the conduction band, and here the hole in the valence band is responsible for the conductivity of this material if we provide the external battery to this material. Okay, so in this case, as I have discussed, the holes which have the positive charge present in the valence band is called the majority charge carrier. The most conduction of this sort of the crystal will be contributed by the holes in the valence band. Okay, so the electrons is called the minority charge carrier. Here in the conduction band, we have less electrons. So, as compared to the holes produced here in the valence band. So, therefore, we call these electrons as a minority charge carrier. So, this was the physics behind the semiconductor materials, and I have discussed that this sort of material have many and many more applications in the modern technology. Okay, and so it is necessary to have knowledge behind that material, and this was the in-depth and the detail theory behind the semiconductor material. Semiconductor material have two types. We have discussed about the semiconductor. They have properties. One is the intrinsic semiconductor with power. All elements are belong to the same all atom belong to the same elements, and we have the extrinsic semiconductor. They have two types. One is the p type, other one is the n type material, and we have discussed all about that. And that's it, guys. Thanks for watching.